Alrighty, hello, and welcome to Chem 400 Office Hours. I can't remember what number week we're in, but we're in it. Hit me up with any questions you may have. I'm here. I'm ready to talk some chemistry. Alrighty. All right, let's talk. Let's talk about finding oxidation states. So I guess Amanda, one question that I have for you. So Amanda, my question for you is it that you find you don't understand the rules for assigning oxidation states, or is it you like see the rules, you know them, but it's that applying the rules is where you're having difficulty? Which one do you find you struggle with? Like you just don't understand what the rules are, or you have seen what the rules are, but you don't know how to apply them? Applying the rules. Okay. Cool. Let's get into let's do some examples then. So let's assign oxidation states. All right, and let's start with how about H2S, dihydrogen sulfide. All right. Now we know that the sum of all oxidation states in a compound has to add to our total charge, and this is going to be the rule that helps us out in every single problem we do. So we know that 2 times the oxidation state of hydrogen plus the oxidation state of sulfur equals our total charge on this molecule, which is 0. That is the first rule. And we're going to use it every single one. Every single oxidation state problem, you're going to write out an equation where it's the sum of all oxidation states in the molecule adds to the total charge. And this, because it has no charge, 0. Now, rule number, I can't remember if it's 2 or 3, tells us about hydrogen. I think it's number 2. That when hydrogen is with other nonmetals, that it will always take an oxidation state of +1. So because hydrogen's with a nonmetal sulfur, it gets an oxidation state of +1. And now that we know the oxidation state of hydrogen, we can plug it in here and solve for the oxidation state of sulfur, because we know 2 times +1 plus the oxidation state of sulfur adds to 0. So we know that 2 plus sulfur equals 0, which must mean, as we solve for sulfur, subtract 2 from both sides, that the oxidation state of sulfur is -2. So for this compound, hydrogen is +1, sulfur is -2. All right, let's do another example. Let's assign the oxidation states for well, how about this? This polyatomic ion. All right. Now we know we're always going to use the first rule, which is the sum of all oxidation states equals our charge. So that means the sum of the oxidation state of aluminum plus 4 hydrogens equals our total charge, which is -1 for this species. Now, hydrogen, we said when it's with other nonmetals, has an oxidation state of +1. But when it's the only nonmetal in the compound, and it is, aluminum's a metal, hydrogen is the only nonmetal. When it is the only nonmetal, it takes an oxidation state of -1. So now that we have our oxidation state of hydrogen, we can solve for the oxidation state of aluminum. Because now we know aluminum plus 4 times -1 equals -1. So aluminum minus 4 equals -1. And now, if we add 4 to both sides, we find that aluminum in this compound has an oxidation state of +3, because -1 plus 4 is +3. So aluminum's +3, hydrogen's +1. Sorry, hydrogen is -1, which is why it has a negative. Let's do another example, and one that maybe will level things up a little bit. All right, H2SO4. Let's determine the oxidation states for each element in sulfuric acid. As I've been doing this entire time, a great place to start is writing out that equation that puts rule number 1 into mathematical form, the sum of all oxidation states. And here I'm going to write a little multiplied sign between 4 and my oxygen so I don't confuse myself and think it's 40. Yes. That is correct. And actually, you know what? Sorry. Let's not do sulfuric acid. There's a better example. It'll be a tad bit harder too, so it'll be appropriate. Let's do sodium bicarbonate. All right, so the oxidation state of sodium plus the oxidation state of hydrogen plus the oxidation state of sulfur plus the oxidation state of 4 oxygens equals our total charge of 0. All right, now there's a rule for hydrogen. We know if it is the only nonmetal, it's -1, but if there are other nonmetals present, it's +1, and we do have sulfur and oxygen. So here, hydrogen will take an oxidation state of +1. We've got hydrogen. There's a rule for group 1A and 2A metals, right? Our main group metals. And you can see that sodium is indeed in the first column. It's a main group metal. And that rule says that when a main group metal is in a, when the 1A and 2A metals, the first two columns, are in a compound, that their oxidation state is equal to their regular ionic charge. Sodium's regular ionic charge is a +1, so we know sodium. Now, we're at a little bit of an impasse because we still don't know sulfur and oxygen yet. We need to determine one of them. Now, when you get, this is where rule number 4 comes in, the last rule. When you have, and this is the one you go to at the very end, when you have two elements, you're going to give the more electronegative element its regular ionic charge. And if you look at the position of oxygen and sulfur on the periodic table, oxygen is higher, which makes it more electronegative. So we're going to give oxygen its regular ionic charge as its oxidation state. And now you'll notice that we have sodium, we have hydrogen, we have oxygen. We can solve for the oxidation state of sulfur. All right, so let's get to work. We have sodium is +1 plus hydrogen, which is also +1, plus sulfur plus 4 times the oxidation state of oxygen is -2. All of these add to our total ionic charge of 0. Now, if we simplify things a little bit, we have sulfur. 1 plus 1 is 2. 4 times -2 is -8. And all of these add to 0. +2 minus 8 is -6. So sulfur minus 6 is 0. If we add 6 to both sides of this equation, we realize that sulfur has an oxidation state of +6 in this compound. So this was the example I was building to. It used all the rules, and we were able to assign an oxidation state to each and every element in this compound. Does that make sense? Let me know if you're tracking, if I'm moving too fast. How are you doing so far? Awesome, awesome. Okay, totally. So are you struggling with like identifying the oxidizing agent, reducing agent, and balancing? Would you like to see some examples along those lines? Alrighty, awesome, awesome. Okay, so let's so here with these problems, we're going to ID the oxidizing agent and the reducing agent, and we're going to balance. Totally. The electron part comes in with balancing, yeah, using the half reaction method. So we'll totally get to that in the third one. Julia, we can totally do some under basic conditions as well. We'll hit it all. Okay, so let's go ahead. Excuse me. Um, the thing to remember, and this can be a little tricky, but the thing to remember about when we talk about the oxidizing agent and reducing agent, the oxidizing agent causes oxidation, and the reducing agent is the species that causes reduction. All right, so as we analyze a redox reaction, we're going to look for the thing that causes the oxidation, the thing that causes the reduction. All right, so let's go ahead and look at an unbalanced reaction. One cool thing is you do not have to balance the chemical equation in order to determine your oxidizing agent and reducing agent. What you do need to do is you need to determine the oxidation states for every element on the reactants and the product side. All right, so here's our first chemical equation. We need to assign oxidation states for each species, and then we'll be able to determine what is being oxidized, what is being reduced. So starting with Mn plus 2 plus, because it's the only element in the species and the total charge is positive 2, manganese, not magnesium, manganese has an oxidation state of positive 2. We can also say the same thing for bismuth on the product side. Now, for bismuth oxide, we've got a little more work to do. So we know that the oxidation state of bismuth plus, the oxidation state of all 3 oxygens adds to our total charge of -1. Bismuth is a metal, oxygen is a nonmetal and a very electronegative nonmetal, so we know oxygen is going to pick up an oxidation state of -2. And now that we know oxygen's oxidation state, we can solve for bismuth. So bismuth plus 3 times -2 equals -1. So bismuth minus 6 equals -1. Add 6 to both sides. And we see that in this compound, bismuth has an oxidation state of positive 5. All right, now let's, oops. So that's a plus 5, that's a minus 2. Let's determine the oxidation state. Sorry, I keep doing this in the wrong layer. Plus 5, minus 2. Let's determine the oxidation states in permanganese. MnO4 with the -1. Now we know the oxidation state of manganese plus our 4 oxygens equals -1. Oxygen's more electronegative than manganese, so it picks up a -2. So manganese plus 4 times -2 equals -1. Manganese minus 8 equals -1. So manganese in permanganate has an oxidation state of +7. All right, now we've assigned all our oxidation states. To determine the oxidizing agent and reducing agent, we need to identify which elements have changing oxidation states. Because remember, in a redox reaction, someone is gaining electrons, someone is losing electrons, right? Gaining electrons is reduction, losing electrons is oxidation. And so the elements that have changing oxidation states are participating in the redox reaction. Now, you'll notice that manganese goes from a +2 to a +7. That's a change. Bismuth goes from +5 to +3. That is another change. So bismuth goes from +5 to +3. That number has gotten smaller, which means there has been bismuth has gained electrons, which means that bismuth has been reduced. Reduction has happened to bismuth. Let's look at manganese. So manganese goes from a +2 to a +7. It has lost electrons, right? Manganese has lost a serious amount of electrons. And because it's lost electrons, that means, I just put lost in parentheses. Because it's lost electrons, that means it has been oxidized. There we go. So manganese has been oxidized, bismuth has been reduced. Now here's the question. So for manganese, what reacts with manganese to cause that oxidation? The answer is BiO3 minus reacts with manganese to cause the oxidation. So BiO3 with a charge of -1, because it reacts to cause the oxidation, this is the oxidizing agent. When you ask the question, what reacts with bismuth to cause its reduction, the answer is manganese 2. So I want to do that in black. Manganese 2, because it reacts with bismuth causing the reduction, is the reducing agent. All right, so that is how you identify oxidizing and reducing agents. First, you assign all oxidation states, find which elements have changing oxidation states, and then for bismuth, we identified that it is being reduced and asked what reacts with bismuth to cause the reduction, Mn2. We saw that manganese is being oxidized. We asked what is reacting with manganese to cause that oxidation, and the answer is BaO3 minus, and that is our oxidizing agent. right, does that make sense so far? Are you tracking? Because the next step is we need to balance this chemical equation, and but which is a totally different thing. So I wanted to just make sure this is making sense before diving into something new. Okay, alrighty. So let's go ahead and look at balancing. Oh, I did that all in one thing. Okay, here, let me just rewrite that real quick. So we have Mn2 plus BiO3 becoming BiO3 plus MnO4. Okay, totally. But hopefully, like, kind of seeing me walk through it gives you kind of the steps of like, okay, this, that, and the other. That's how I go forward. That's what I do at each phase. Hopefully. All right, now let's go ahead and balance this under basic conditions. All right, which is the harder of the two. Now, we're going to use the half reaction method here, and the half reaction method for balancing chemical equations goes like this. Step number 1, you have to split your reaction into 2 half reactions. Step 2, you need to balance your atoms for each half reaction. Step 3, you have to balance your charges for each half reaction. And step number 4, you need to balance your electrons for each half reaction. The 5th step, once you've done these, is you recombine. You recombine your 2 half reactions into one, and that will be your balanced chemical equation. So, excuse me, when I look at this, we have 2 half reactions in play. One is the half reaction with manganese. The other is the half reaction with bismuth. And the way you know to break it up this way is because your 2 half reactions will involve the element that gets oxidized and the element that gets reduced. We already did that in the previous step. So we know that the bismuth species go together and the manganese species go together. It doesn't matter which one you start with. Oops. I'm going to start with bismuth. All right, excuse me. So BiO3 minus becoming just bismuth 3. Now, first we got to balance our atoms, all right? On our reactant side, we have bismuth and oxygen. On our product side, we have just bismuth. Excuse me, there's not 3 of them, there's just 1. But we need oxygens if this thing's going to be balanced. Now, whenever you're doing the half reaction method, and your oxygens are out of balance, you always balance oxygens by adding water. So since we have 3 oxygens on our reactant side, we need to add 3 water molecules to our product side. This balances our oxygen, but has the unfortunate side effect of adding 6 hydrogens. The way you balance your hydrogens is by adding hydronium, H plus ions. We have 6 hydrogens on our on our product side, so we need 6 on our reactant side. So we had 6 H plus ions, and now we're balanced. The problem is H plus is an acid, and we are under basic conditions. So if we were under acidic conditions, you've balanced your atoms, you'd be done. But we're under basic conditions, so we're not quite done. H plus does not exist in any measurable, or I should say appreciable quantity in a basic solution. We can use it to balance our hydrogens, but then we have to undo it right after we introduce it. Now, how do you undo something like that? Well, you're going to use a neutralization reaction. H plus combines with hydroxide. Hydronium reacts with hydroxide to produce H2O. So if you have 6 hydronium, you can fix this by adding 6 hydroxide ions to both sides of this equation. The reason why we're doing this is because these 6 hydroxides combine with these 6 hydronium to make 6 molecules of water, which totally exists in a basic solution. When we rewrite it, then we have 6 molecules of water plus bismuth BiO3 minus becomes, sorry, that's not a bromine, BiO3 plus, excuse me, 3H2O plus, sorry, I have no idea why I wrote an X here. Should be 6 hydroxides. All right, now you may notice that we have water on both sides of this chemical equation. You could cancel it now. You could wait to do it at the end of the problem. I prefer to just take it out now because it's less writing. These 3 waters will cancel 3 of these. So our half reaction for bismuth with balanced atoms is 3 water molecules plus 1 BiO3 minus produces bismuth 3 plus 6 hydroxides. All right, and this is just balanced atoms. We still need to balance our charges for this half reaction. So we have our atoms. Let's balance our charges. Now, when you're balancing charges, the only thing you can add to either the reactants or the product side, the only thing you can add are electrons, is an electron. Now, when we look at this reaction, we have a total charge of -1 on our reactant side because water has no charge. BiO3 minus has a charge of -1. On our product side, we have a +3 for bismuth minus 6 for the 6 hydroxide. So the reactant side has a total charge of negative 3. Sorry, the product side has a total charge of negative 3. The reactant side has a total charge of negative 1. We are going to need to introduce 2 electrons to our reactant side so that we get negative 2 minus 1 equals negative 3. And now our charges are balanced on both sides of the bismuth half reaction. So we did atoms, we did charges for bismuth. Before we can balance electrons, we have to balance our other half reaction with manganese. So let's go ahead and take a look at that half reaction. So our manganese half reaction is Mn2 plus going to MnO4, the negative 1. I do not mind at all. Do not mind at all. So let's take this just a little slower. All right. So we need to balance our charges. All right, let's take a look at our charges. So on our reactant side, oops, hang on. Sorry, Photoshop is, okay, there we go. Sorry, Photoshop temporarily froze, but now we're responding. So water has a charge of 0. BiO3 has a charge of negative 1. So on the reactant side, our total charge is negative 1. Let's look at the product side. Bismuth has a charge of positive 3. Hydroxide has a charge of negative 1, but we've got 6 of them, so this is a total charge of negative 6. 3 minus 6 is negative 3. So on our, and this is the important thing to keep in mind, you're comparing the charge on the reactant side to the charge on the product side. The reactant side has a charge of negative 1. The product side has a charge of negative 3. We need, just like we have to balance atoms, we need to make sure that our charges are balanced, that there's the same charge on both the reactants and the products side of the reaction. The only thing you can do to change the charge using the half reaction method is by adding electrons. Okay, awesome. And so, just for completeness sake, the way we do this is we add 2 electrons to the reactant side. So now our charges are, we've got negative 2 plus 0 minus 1, which gives us now a charge of negative 3 on our reactant side and our product side. And this is balanced. All right, so that's what that was all about. Now we're going to do the exact same thing to the manganese half reaction, where we're going to balance atoms and then charges, and then we'll get to what this balancing electrons business is. So first we need to balance our atoms. There's 1 manganese on our reactant side. On our product side, there's 1 manganese and 4 oxygen. You always use water to balance oxygen atoms for redox problems. So you add 4 water, which unfortunately introduces 8 hydrogens. You balance that. using hydronium, H+. Now we know we can't keep our hydroniums because we're in basic conditions. Oh, sorry. This is 8 hydroniums. So we're going to add, for each hydronium, we're going to add a hydroxide. And our reason for doing this is that 8 hydroxide plus 8 hydronium turns into 8 molecules of water. Which gives us, now our atoms are completely balanced and the basic conditions have been accounted for. Again, you'll notice that we have 4 water molecules on our reactant side, 8 on our product side. I'm going to cancel now. So our manganese half reaction is 8 hydroxides plus manganese, 2, makes permanganates plus 4 molecules of water. Now we need to balance our charges. Sorry, permanganate has a charge of -1. So let's look at our charges. We have 8 hydroxides, so that is a -8. Manganese 2 has a charge of +2, so our total charge is -6 on the reactant side. On the product side, we only have permanganate, which has a charge of -1. So we got to use electrons to balance this half reaction. And let's see, it looks like we need to bring in 5 of them so that we have -1 minus 5, which equals -6, and now we have balanced charges. So atoms and charges both balanced for our manganese half reaction. So I'm just going to rewrite this. 8 hydroxides plus manganese. 2 produces permanganate plus water. All right. Oops. Sorry, I meant to do this in a different layer. So now we have our manganese half reaction. And our bismuth half reaction. Yeah, we have 4. I'm like, yeah, we got 4. Except I didn't write it with 4. Good catch. That would have thrown us off in the end. Yes, 4 water molecules there. All right. So now, and actually, I want to line these up a little bit better. All right, now. At this moment in time, we have split our reaction. We've balanced atoms, we've balanced charges. What is this balancing electrons thing? Well, the deal is the number of electrons consumed in a redox reaction must equal the number of electrons produced. You'll remember that in a redox reaction is like a drug deal where the electrons are drugs. You don't see who's selling, you don't see who's buying. It looks like everybody's just doing normal things. So we need to make sure that the number of electrons produced equal the number of electrons consumed. In other words, this number of electrons needs to equal this number of electrons. Now 2 does not go into 5. So we need to multiply everything in our first half reaction by 2 and everything in our second half reaction by 5. So this will change things so that we're left with, let's see, 2 times 8 is 16 hydroxides plus 2 manganese 2 ions producing, so it just looks confusing. There we go. Producing 2 permanganates plus 8 water molecules plus 5 times 2, this is the whole reason why we're doing it, 10 electrons. This produces 5 times 2, which is 10 electrons. Now working the second half reaction, 5 times 3 is 15 molecules of water plus 5 of these BiO3 minus ions, producing 5 bismuth 3s plus 6, no, sorry, 5 times 6, so 30 hydroxides. All right. Now that our electron count is balanced, we add these two together and cancel anything we can. So if we've done our job right, all the electrons cancel. But you'll notice we have 8 water molecules over here and 15 over here. So 8 of these cancel, leaving us with 7 on our reactant side. Similar situation arises with hydroxide. We have 16 up here and 30 down here. So 16 cancel, 16 of these cancel, leaving us with 14. So our balanced chemical equation is 7 molecules of water plus 5 molecules of BiO3 minus plus 2 manganese 2s produce 2 permanganates plus 5 bismuth 3 ions plus 14 hydroxides. And that is sloppy. That is the balanced chemical equation. So that is going through every single step of the half reaction method, splitting it, balancing atoms, charges, and electrons, and then recombining to get your balanced chemical equation. Alrighty, and that's about it for office hours. We definitely don't have time to do a second one of these in the 5 minutes that are remaining. But if you have any last questions, let me know. Dude, Amanda, you are so totally welcome. Thank you for making office hours interesting today. There have been some where I'm just kind of sitting here sad and alone, and I would much rather be talking about chemistry. Alrighty. If there are no further questions, I think I'm going to go ahead and shut the stream down. I can hear I have a 3-month-old who is crying a couple rooms over. I can hear him. Looks like he woke up from his nap a little bit early. But thanks for hanging out. This was awesome. Getting into some chemistry, and we will we'll hit it up next week. So Julia, anytime that you're dealing with, and we don't have enough time left in office hours to like work a problem, but anytime you have a gas that is expanding or being compressed, you'll need to calculate the energy change with respect to work, because energy change is equal to the thermal energy change plus the energy absorbed or released through work, and work is equal to -1 times the constant atmospheric pressure times the change in volume in this delta V. First is, we know that a delta is final minus initial, but this is for a gas. So anytime you have a gas expanding, that's a change in volume, or a gas being compressed, that's a change in volume. Against a constant pressure, then you'll have an energy change, with through work.